Hey guys, in this video I want to introduce the notion of triple integrals. Given that this is the first time we are looking at triple integrals, I'm going to focus on the case when it is defined over a rectangular box. Alright, so what is a rectangular box? Well, this is a set of points in space such that each of the variables x, y, z are bounded by constants. So here the numbers a, b, c, d, r, and s are fixed constants. The aim is to define the triple integral of a three-variable function f over this rectangular box. To do this, we first divide the rectangular box B into sub-boxes by dividing the interval AB, CD, and RS into sub-intervals of equal length. Let's say delta x, delta y, and delta z respectively. So here's a picture of the rectangular box B together with its partition. Notice that we can represent one of these boxes by B sub ijk, where the index ijk come from the interval x minus I to xi, yj minus 1 to yj, and the interval zk minus 1 zk. In other words, these are the intervals that gives us the rectangular box bijk. Now the dimension of this box is delta y, delta x, and delta z. So the volume of bijk is just the product of its dimensions, namely delta x times delta y times delta z. And this must be the same for all the rectangular subboxes we have. And in general, we're going to denote this by delta v. The capital V here represents the volume of this subbox. Right, in the next step, we shall form the following Riemann sum. This is a triple sum since we have to sum over the index I, j, and k, which are allowed to vary independently. Basically, for every subboxes bijk, we are going to pick a sample point and evaluate our function at this sample point. The resulting value will be multiplied by delta v. And summing these values over all possible combinations of ijk, we arrive at this Riemann triple sum. Finally, in the last step, we are going to take limit of this Riemann sum. So in particular, we are computing the limit of the Riemann sum as the upper bound for the index ijk tend to infinity. In other words, we are computing the limit as we make the partition of our rectangular box smaller and smaller. Provided this limit exists and is independent of the choice of the partition as well as the sample points, then this will be called the triple integral of our function f over the rectangular box B. Now in practice, we almost never compute any triple integral by using the definition. Indeed, we often make use of what we call the Fubini's theorem to evaluate any triple integral over a rectangular box. Well, basically the theorem says that if the function is continuous on the rectangular box B given by the respective intervals, then this triple integral can be computed by evaluating the iterated integral with respect to the underlying variables given here on the right hand side. Notice that the order we have chosen over here for the iterated integral is the order dx, dy, dz. Actually, the order does not matter since all of these variables are bounded by constants. However, if we have chosen the order dx, dy, dz, then we have to make sure that the corresponding integrals have the right lower and upper limits bounding the variable. So here in the most outer integral, we have the variable z being bounded between r and s, the middle variable y between c and d, and the most inner integral is an integral with respect to x from a to b. Okay, let us look at one example. Suppose we want to evaluate the triple integral of the function x, y, z squared over the rectangular box B given as follows. Well, by Fubini's theorem, we can evaluate this triple integral by evaluating the iterated integral with respect to the underlying variables. Here I have chosen the order dx, dy, dz, in which case the variable z, which is placed at the most outer integral, is bounded between 0 and 3, the variable y between -1 and 2, and the variable x lies between 0 and 1. Right, we are going to evaluate this by first computing the most inner integral with respect to x. So by regarding the variable y and z as constant, the antiderivative of the function with respect to x is x squared over 2 times yz squared, where the lower bound for x is 0 and the upper bound is 1. Therefore, by substituting the upper and lower bounds into the antiderivative, we have the resulting iterated integral with respect to y and z, where the function now is just y times z squared over 2. Next, we are going to compute the inner integral with respect to y. Doing this, we'll have y squared times z squared over 4, where the lower bound for y is -1 and the upper bound is 2. Hence, after some simplifications, we have z squared minus z squared over 4, which is 3z squared over 4. Therefore, the final answer is just the antiderivative evaluated at the lower bound z equals 0 and the upper bound z equals 3. And this will give us the final answer, which is 27 over 4. Okay guys, that's all for now. Next time we shall look at triple integrals over more general region in space. Stay tuned.